All right, thank you very much. So I actually got a pretty good setup earlier from Paul as well as the speakers earlier in the session, so thank you very much. So I'm going to be talking about actually trying to observe exoplanetary radio emission and how we can incorporate some saturation effects that we see in Earth's ionosphere into those calculations. So for a bit of background, the auroral radio emission is observed from all magnetized solar system planets. So we have a composite image of Jupiter here. So this is the aurora, I think, in UV. And the radio emission actually occurs farther up these field lines. So they have the same footprints, but they occur farther up. A very nice feature of this emission is that for exoplanet, it would have a very favorable contrast between the star and the planet compared to visible light. So I'm pretty sure that Jupiter is one of, if not the brightest radio object in the sky at Earth, as seen from Earth. And so if you can detect the emission, then it would be a very good detection mechanism for exoplanets. So for the emission itself, it has two very interesting features. One is that it's highly circularly polarized, which just means it's easier to pick out among other radio sources. And also, as was hinted at earlier, the signal frequency is dependent on the magnetic field of the emitting region. So that means if you get the signal at all, then you're getting a direct measurement or an indirect measurement of the magnetic field of the exoplanet. So that's why it's of great interest to the exoplanet community. And so for solar systems, there exists this scaling law called the Radiometric Bode's law. And essentially what it finds is that the amount of radio power you expect is linearly proportional to the amount of solar wind magnetic power incident onto your magnetosphere. And so you can see that it actually works incredibly well for the solar system planets, which are the solid circles, and even some of the Galilean moons. And so that's looks quite promising. And so what people have done is they've extrapolated that to the regime of Jupiter's. And so as you move your Jupiter closer to your star, you're going to increase the incident magnetic power of the solar wind. And so you get these really high radio powers as a prediction. And so some of these even fall within the detectable range of current radio telescopes, and that's very exciting. And there have been a handful of observation campaigns looking for such signals, and yet so far we have not found any. So there are a couple of reasons why this could be the case. It could be that we have poor solar wind constraints. It could be because we're overestimating the exoplanetary magnetic fields, or outside of the beaming angle. It's a very concentrated signal. And these are all possible, but it's doubtful that this accounts for all of them. So one theory that is actually pretty interesting is that the signal can be absorbed by either hot Jupiter with a very strong planetary wind or by the stellar wind. But what we want to explore is the possibility that we're just simply overestimating the predicted radio flux. And so that leads to the question of what can cause a nonlinear relationship between the solar wind and the resulting radio signal. And then that brings us to which was just brought up in the past talk, saturation effects as you increase UV. But in terms of Earth, we look at it as the saturation of the ionospheric potential. And it's observed at Earth not during normal solar wind conditions, but during solar storms. So essentially what you have, I won't go too much into the equation, but essentially your solar wind has an effective potential drop across the magnetosphere. And then that potential drop is communicated to the ionosphere via alphane waves. But it turns out that there is a transmission coefficient that depends on both what we can think of as the solar wind conductance and the ionospheric conductance. And so this plot shows phi sub m, which is the solar wind potential, and is quite linear for low magnetic field strength, IMS strength. And then as you increase your solar wind magnetic field, your actual potential in your ionosphere will saturate and cap off. And so that can occur this occurs when sigma A is much less than sigma P. So that happens usually at Earth because you have a very large solar magnetic field strength. But for exoplanets, this can occur just because your planet is so much closer to your star that you're going to get more UV flux, and therefore your sigma P is higher, and you're much more likely to be in a region of saturation. So why does this matter for radio? Because your potential is directly proportional to your magnitude of field aligned currents. And to kind of explain this a bit more, essentially, if your field aligned current is above a certain threshold, then you're required to accelerate electrons in order to support that current, and that acceleration of electrons into your magnetosphere combined with the magnetic mirroring effect is what sets up the instability that results in the radio emission. And so we can compare this saturation model, this analytic saturation model, to what RBL predicts for not we, but Nichols and Milan have, for 3 theoretical Jupiters with magnetic field strengths of 0.1, 1, and 10 times the strength of Jupiter's field. And so there's a lot going on here, but to sort of sum it up, the x-axis is orbital distance, so we're just dragging this through the solar system, and you can see that once you get lower than Mercury's orbit there, about 0.4 AU, you get your ionospheric conductance greater than your solar wind conductance, and therefore you end up in a region of saturation. And the shaded area here is the region that most hot Jupiters reside in. And so we can jump down to this plot and see that RBL predicts radio powers about 2 orders of magnitude greater than what the saturation model predicts. So this could be a reason why we have not observed any radio emission from exoplanets yet, when we were expecting, or we could just barely have enough sensitivity to reach these levels. And so if you know anything about modeling planetary magnetospheres, you know the next step is to do MHD, and so that is what we have done. We are trying to take the steady state models and add in more dynamics to them. And so we're using this sort of new coupled code Gamera MHD model with RCM and mix. So Gamera is a new model, so you need to advertise a little bit. And so Gamera handles the solar wind coupling to the magnetosphere, and then that couples to your ionosphere. And this naturally counts the saturation behavior naturally counts for the saturation behavior just due to the way you're solving the equations. And then what we're interested in for backing out the radio power is the Rice convection model, which simulates the inner magnetosphere, which tracks the field aligned currents as well as the electron energies and densities, which is what you need to compute the radio power you expect from your field aligned current strengths. And so what we're going to do is we're going to test this out for an Earth case for now. Like I said, this is a relatively new model, so we want to confirm it in a region where we expect the models to have a pretty fair amount of agreement. And so we are going to expect mild saturation effects, but nothing too extreme. And this is what we end up with. And so ignoring the top plot for now, we have the total power, the total radio power predicted by Radiometric Bode's law, the analytic saturation model, and then from our modeling setup. So the orange line is the raw data, and then the black line is the total amount of power if you integrate the previous hour of observing time, which is much more realistic to what you would observe with radio telescopes. And so to compare those 3 at the bottom, we find that at the back end of the storm, when everything's sort of settled down, the models are in fairly good agreement. You'll find that the analytic saturation model always predicts less than RBL does, which is what you would expect. And we sort of fall somewhere around that range. But what I wanted to point out was during the storm itself, we actually get a larger expected radio power. And I want to especially point out this peak right here, where we jump up about 2 orders of magnitude greater than what you would expect just looking at the solar wind values themselves. And the reason why that occurs is because you have a strong switching of a northward IMF to southward, and what that does is essentially you're both injecting a lot of plasma into your magnetotail, and you're also compressing. You have a lot of elongated field lines that are now injecting in and accelerating those particles. And so that's something that pops out through that dynamic interaction that you don't get from the analytic expressions. And also another interesting feature is at the very beginning here, where the other two models see a decrease, we actually see an increase in the expected radio. And that is because this is at the storm onset where you're compressing your magnetosphere. And so according to the analytic equations, because you have a smaller cross-section, you're going to get less radio. But because you're compressing your magnetosphere, you're also driving these other currents. And so we're accounting for these other sources of current that can lead to radio, and not just the pure solar wind transmission behavior. And so just to show you what the model results look like, we have a little movie. And so to orient yourself, the sun is in this direction, and here's your sort of your ionosphere view. And so again, like I said, the emission actually happens along the field lines. So what we're actually going to see are the foot points of those field lines where the emission is happening, and color coordinated accordingly. And so what you'll want to look for, especially during the increases of power here, is a lot of injection along the tail. And then once it's in the system, it sort of drifts around westward. Comes in the tail, you have, so it occurs all around, but the points of very strong radio are due to this strong interaction in the tail. Okay, and so the three main takeaways is that for typical hot Jupiters, using the ionospheric saturation model, you're going to predict radio emission signal about 100 times less than what radiometric Bode's law predicts, since that's what is traditionally used, and we can barely detect that range. This can explain why we haven't found anything so far. The ionospheric saturation model depends very strongly on the ionospheric conductance, and so that's determined by both what you're ionizing and how strong you're ionizing it. So understanding these two components are very important in constraining this model to give us better predictions in the future. And so we're sort of looking for a bit of hope of being able to detect these sooner by adding in the numerical modeling and seeing if there are any dynamic effects that can then drive the signal back up into potentially transient signals that we could actually detect. Thank you.